So guys, this is always kind of an interesting day in this class. And I mean that in two ways. It's interesting because it's interesting, but it's also interesting because frankly, I have no idea how this day is going to go down. Typically, I can go into a concept and I can think, I have the big picture, 60 minutes from now, this is basically the path that we're going to take through the material. Guys, honestly, this isn't one of those days. Because we know so much backstory in terms of the way molecules form, we'll see. We're always going to get to the same place, which is you will understand what hybridization is, you will understand how to predict the hybridization of atoms in a molecule, and you will understand the significance of hybridization as it applies to double and triple bonds. So let's say that again. You will understand how hybridization happens, you'll understand how to predict the hybridization of atoms and molecules, and you will understand the significance of hybridization as it relates to double and triple bonding. We're going to get there before 1225. Frankly, I'm not exactly sure how we're going to get there because a lot of it's going to depend upon where you all take this conversation as we get into it. But guys, the safest place to start the conversation as a jumping off point is connecting this to Lewis dot structures. And guys, I would suggest you don't write any of this down until we draw a Lewis dot structure coming up next. So guys, we understand that Lewis dot structures do a really good job of explaining structure. Who's bonded to whom? Where are the unbonded pairs? We understand they're not three-dimensionally accurate, and therefore we need to know shared and lone pairs in domain theory. But guys, what they don't tell us about is how these bonds actually form. We know that it's sharing in regions of increased electron density, but guys, they don't answer a very fundamental question. And the fundamental question is actually, how do these bonds form in places where seemingly they shouldn't? So guys, to get this started, do this with me. Draw a methane molecule. Scratch it into your notes. Draw yourself a methane molecule. You got it? You should be close. You good? What's the domain geometry? Tetrahedral. What's the molecular geometry? Also tetrahedral because all the domains are bonding domains. Now, off to the side, write the Lewis dot structure for carbon. Do you now see the problem? What's the problem? Compare the Lewis dot structure for carbon with the Lewis dot molecular structure for CH4. What's the problem? All right, I'll draw it. So guys, here's what we got. Come on, pen. Oh, look at my pen. I don't know. Just got lucky. See the problem? Guys, we know that carbon's got 2 electrons in the s, specifically here the 2s, and 2 unshared or 2 unpaired electrons in the p. If we draw the orbital filling diagram for this, we know that carbon's Lewis dot structure actually, or its orbital filling diagram looks like that. So why is that a problem relative to methane? Well, guys, carbon's only got 2 bonding sites, right? In order for a bond to form, there's got to be some sharing of electrons. And you all sort of have this concept that hydrogen comes in and it shares an electron, and another hydrogen comes in and it shares an electron, and now it's game over. So now some of you are starting to think, well, okay, but we've sort of talked in class that these coordinate covalent bonds, and I don't remember if we talked about them here or in lab, you could maybe in theory put another hydrogen there in the same way that the ammonium molecule forms. Remember, ammonium is NH3, or ammonia is NH3, but a hydrogen can come along there and bond to those electrons, even though it doesn't bring one to share, and that forms ammonium, but that still doesn't get us CH4. Because even if we stick another hydrogen on there, we only get CH3. Do you see the problem? So guys, how did we fix this last year? Do you remember? What did we do? We just said they spread out. You may even remember it. I remember it well. It was right here on the screen. And I had you draw the Lewis dot structures for 5 atoms. And the last one that I had you do was carbon. And you drew this with the 2 in the S and the 2 in the P. And then I crossed it out and it said spread them out. And then we drew the carbon with each of the electrons spread out. Do you remember that? And then we had 4 bonding sites. And then I said, this is what carbon actually did. And in some of my classes, my students asked why. And I said, we'll talk about it next year because the answer is hybridization. Guys, today we're going to talk about the answer. Why is it that carbon can form 4 covalent bonds when it only has 2 bonding sites? And guys, the answer is hybridization. So let's talk about hybridization. So guys, when we go back and when we look at the Lewis dot structure for carbon, where are the electrons that are on top? Where are they? In the S, right? What about the ones that are left and right? They're in the P. Which ones of those form covalent bonds? The S's or the P's? Neither. Guys, this is where we're going with this. The S orbitals and the P orbitals are not the orbitals that are bonding in carbon when it forms covalent bonds to form things like methane. So what is going on? Well, guys, we'll talk about it in many different ways. But guys, what is going on is this. The electrons in the S and the electrons in the P actually meld together. What happens is the S orbitals and the P orbitals, forgive me. Hi. Hi. Thank you. The S orbitals and the P orbitals, guys, actually mate together. And they have like orbital babies. And the orbital babies that they have are what are called hybrid orbitals. And literally, you can think of them as being like the children of the S and the P, in the same way that my children kind of look like me and kind of look like my wife. The S and P, when they blend together, they form hybrid orbitals that kind of look like the S. And guys, what do the S orbitals look like? Spheres. And they kind of look like the P's, which look like dumbbells. And when they meld together, they form these hybrid orbitals. And in this case, these are what are called sp3 hybrid orbitals. Now, where does the name come from? Well, guys, how many S's and how many P's melded together? And the answer is all of them. One of the S's and all 3 of the P's in carbon blend together. And they make 4 sp3 hybrid orbitals. And then what happens is these electrons spread out through those hybrid orbitals, and it's those hybrid orbitals that actually create the covalent bonds in methane. Yeah. Absolutely. And that's where this is headed. Guys, these don't have to everybody get involved in hybridization. And sometimes what you'll find out is that some of the P's will not hybridize. Guess what that leads to? Bless you. Double and triple bonding. And guys, we're going to talk about that in a moment once we get into the details. But guys, in order for double and triple bonds to form, you've got to have P orbitals that have not hybridized. So guys, the S will always hybridize, and then the P's can or will not hybridize depending on the particular molecule. And when the P's do not hybridize, they are available to form double and triple bonds. Yeah. Exactly. So these numbers are telling you how many have hybridized. So last time? Yeah. Oh, good. Okay, so what can happen then, guys, is we can have sp3 hybridization if they all hybridize. And if we do, how many hybrid orbitals do we get? 3 plus 1 is 4. Get the idea? So these numbers, for every orbital that we put in, a hybrid orbital comes out. So if we have sp3 hybridization, we will get 4 hybrid orbitals. We can think of 1 coming from the s and 3 coming from the p's, and they all look the same, and I'll show them to you in a minute. But we can also have this. We can have sp2 hybridization. And when something hybridizes sp2, how many hybrid orbitals will we get? 3. And we can also have sp hybridization. And when we have sp hybridization, how many hybrid orbitals will we get? 2. But we can also have sp3d hybridization. And when we get that, how many hybrid orbitals will we get? And then the last option is sp3d2. And when we have that, we will then have 6 hybrid orbitals. Now, guys, for some of you, you're starting to see what's going on here. But I'm going to reorganize these, and then I think you're going to get it. So here they go in order. sp, sp2, sp3, sp3d, and sp3d2. Now, when we get this, we get 2, 3, 4, 5, and 6 hybrid orbitals. But guys, you ready for the aha moment? I'll let you catch up. You ready for the aha moment? Guys, you already know about hybrid orbitals. We've just never called them that. We used to call them domains. Guys, the electron domains are the hybrid orbitals. Notice that what we did last time, right? Well, we graded it last time. When you learned the molecular geometries, you learned linear, 2 domains, trigonal planar, 3 domains, tetrahedral, 4 domains, trigonal bipyramidal, 5 domains, and then octahedral, 6 domains. Guys, those domains that you already understand as a result of knowing the 3-dimensional geometries are the hybrid orbitals. And that's how we're going to treat this. You ready? This is what you've got to be able to do on the test. If you can do this, you're just fine. And it goes like this. Here's methane, right? You already told me what is its domain geometry. Tetrahedral. Guess what? That carbon is sp3 hybridized. That's all you got to be able to do. Done. I'll give you your homework. Because that's it. That's all the more conceptually challenging. We're not done, but that's functionally all you've got to be able to do for the test is count domains. If you've got 1, 2, 3, 4 domains, 4 domains results from 1s and 3 p orbitals hybridizing, and that would be sp3 hybridization. You get the idea? So the thought then, guys, goes like this. Back to that list. What do we call the molecular geometry of something with 2 domains? Linear. Anything that is linear is an sp hybrid. What do we call 3 domains? Trigonal planar. And here we can even write these down over here. This is linear. Anything that has 3 domains is trigonal planar. Anything with 4 domains is tetrahedral. Anything with 5 domains is trigonal bipyramidal. And then anything with 6 domains is octahedral. That's it, guys. All you have to be able to do is identify the hybridization based upon the domain geometry. That's all they will ask you for on the AP test, is to go, hey, if that's linear, it's an SP hybrid. If that's trigonal planar, it's an SP2 hybrid, and so on. And the way to know is just understand that there's an understood 1 above the S, and then add the numbers. 1 plus 1 is 2, 1 plus 2 is 3, 1 plus 3 is 4, 1 plus 3 plus 1 is 5, 1 plus 3 plus 2 is 6. That's all you got to be able to do. Because every orbital that goes in, a hybrid orbital comes out. Do you understand the concept? Are you okay with the application? That's all you got to be able to do, guys. The reason that I do this first is because if I can put to rest your concerns that the concepts are difficult, and if you really trust that this is all that you need to be able to do, because it is, then you can just enjoy the rest of the day and understand how really cool this stuff actually is, with the understanding that functionally this is all you've got to be able to do. You okay with the practice? So guys, let's do this then. Let's just make sure you're okay. Ammonia. What's the hybridization of the nitrogen? How many domains? Okay, so it's tetrahedral. Is this a domain? Yeah, it's not a bonding domain, but it's still a domain. So what is the domain geometry? Tetrahedral. So what's the hybridization? sp3. It just so happens that one of those sp3 hybrid orbitals is full. If you look at it this way, here's the s, and here's the p's, and it would look like this. So that would be the orbital filling diagram for the valence electrons in nitrogen. When that forms sp3 hybrids, when you put 5 electrons in there, there's 4, there's the 5th. This hybrid orbital is full, and the other 3 are available for bonding. Well, in nitrogen. But that's important, Spencer. The thing you've got to understand, guys, is this hybridization process happens before bonding. So the smearing of the S's and the P's happens, and then these these sp, in this case 3 hybrid orbitals, are available for hydrogens to come in and form covalent bonds. Go ahead. Oh, I don't know, but forgive me, it doesn't matter. It doesn't matter where they originated from, because it truly is a blending together. They lose their S identity and their P identity. They sort of forget where they came from, and they fully accept this new existence. Yeah?
So we have like 2 S.
Yeah.
So is there like 2 S?
Hold on, 3.
No. So we've got like our different levels. So
Yes.
We got like S or 2P.
Yeah. Right. Yeah, but
These do those get labels?
no. So I see what you're saying. So like these are 2s and these are 2p. We don't think of them that way, because we always understand that they're valence. So whatever the valence shell is, that would be these guys. The place where I've never thought of it this way, but if you go back here and you think about this, this would necessarily have to be at least 3, because that's the first place we see a D. But other than that, we don't really think about it. Yeah. That is a brilliant question. So guys, the question on the table is, why does it stop at D2? Why can't we get D3 and have 7 hybrid orbitals and things like that? And the answer is because there physically isn't space. Just a second, Spencer. So if you think about it, you think about an octahedral structure. Okay, so you've got a central atom, and then you've got 4 in the, what we could think of as the equator, although it really isn't because they're equivalent. But you've got 4 here and then 1 here and here. The problem is that as you start to think about moving more atoms around that central atom, like let's bring a 7th. The problem is that the repulsion of those 7 nuclei around that central atom becomes so great that it becomes unstable and it falls apart. So the maximum that you can create stability is by placing 6. That said, there are other ways to do this that don't involve hybridization. You guys may have done this at the U, where there's a whole nother type of bonding that can take place, which is it's called ligand field theory. It's really interesting stuff, where you can actually create compounds, they're actually complex ions, where you can put more than 6 things around a central atom. But we think of it as a different type of bonding that we don't describe as being covalent. The limit with covalent bonding is 6, and then they just create so much interference they fall apart. Just a second, go ahead.
So, is that what you were just barely getting into about like 1 through 6? Is that explained in how manganese and chlorine and all these other atoms like this?
Yeah, because like if you look at manganese, it has an oxidation state of 7, right? Which would begin, that's a neat observation, Spencer. You would start to understand that manganese can do something in 7 directions. But it's a different something. It's not a covalent bond. It's described by this thing called ligand field theory and complexation, which is a whole nother creature that we don't get into. Just a second, Jared, go ahead.
So is it because of that reason there's not enough space that we can't do covalent bonding, like using the F sublevel?
Gosh, I don't know. I'm frankly not sure. It may be energetics too, but I really don't know. Right, right. Can't we get into the F's? And frankly, I've never seen the math of it. I don't know. The one thing that would argue for we should be able to do the F's is by the time you get down to the F's, these atoms are so big that they could have enough surface area that you could get more than 6 things around it. I've just never been exposed to F electrons getting involved in valency. It doesn't mean it doesn't happen. It's just not a part of what I've experienced. So go ahead. Oh, really? Yeah, and it just doesn't. So guys, here's where we are right now. Let's put our concerns to rest. All you've got to be able to do is predict hybridization. You will predict hybridization based upon domain geometries. 2 domains, linear, that has to be SP. 3 domains, trigonal planar, that's SP2, and so on. You guys all okay with that? Okay. Now what I want to do is I want to show this to you visually, and then we're going to ask kind of an interesting question about where this is all headed. Guys, this is actually a flash animate. Well, it's not. It's flash video, and it gets a little garbled. You'll see. Get out of this. I'm just gonna. Well, I'd better just quit this so it doesn't get confused. Okay.
In the 1930s, Linus Pauling
I've
introduced
in
the concept of
here, let me just
hybridization.
mute this. So guys, we understand that we have the s and the 3p orbitals. And notice down here we have the option of selecting each of the different types of hybridization. So for example, let's go with sort of the safe choice. Let's go sp3. So if we choose sp3, all 3 of these will hybridize. How many hybrid orbitals will we get back out? 4, and those 4 hybrid orbitals will be oriented how? Tetrahedrally. So here we go. The S and the 3p hybridize together. When they do, they create 4 hybrid orbitals. These 4 hybrid orbitals located around the same nucleus take on a tetrahedral shape, and that explains tetrahedral domain and then sometimes molecular geometries. Now guys, the thing that I'm not sure, and I can't pause the video unfortunately, so I'm just going to have to call your attention to it and then play it again. We said that the hybrid orbitals, right, kind of look like mom and kind of look like dad. Mom is a sphere, dad is a dumbbell, in this case 3. So what does that look like when you have a sphere and a dumbbell blending their characteristics? Well, did you notice that when these things first showed up, they had a large lobe and then a smaller lobe? That's what that blending together looks like. That the average of a sphere and 2 dumbbells is actually one large dumbbell and then a smaller lobe that we call a degenerate orbital. So we have the major lobe, which is the one that gets involved in bonding, and then we have that minor or degenerate, you don't need to know that term on the test, but that degenerate lobe that is actually not involved in bonding. And you'll notice when we brought them together, they didn't even represent the degenerate lobes because in fact they aren't important to our understanding. They are in theory still there, and the electrons can spend a little bit of time there, but they aren't important to our understanding of structure. So again, if we play this again, the S and the 3 P's hybridized together, there you can see the degenerate lobes, which we don't represent, and there's our tetrahedron. Do you get the idea? Okay, now let's do this. The next one that I want to show you is sp2 hybridization. So we've got 1 S and we've got 3 P's. When we sp2 hybridize, what happens to the p orbital that doesn't get involved in hybridization? What you're going to see in the animation is it just fades into the background as if it ceases to exist. That is not the case. We're going to look in a minute at what happens to that unhybridized p orbital, and I think you're going to find it fascinating. But let's do this first. So the S and the 3 P's, did you notice what they did? That p just sort of fades out. It doesn't just fade out. It's still there. It just doesn't hybridize. So these 3 hybridize together. How many hybrid orbitals do we get? 3. And these around the same nuclei explain a trigonal planar structure. You okay? Is it pertinent to this?
Yeah.
Go ahead.
So, they look the same as sp3, like the exact same.
They do.
Like,
Yeah.
Shape, like, not even just shape-wise, just size-wise.
Absolutely. Yeah, they are, because they're still just regions that electrons occupy. Yeah, definitely the case. Yeah.
So, like, it's not like more P's will make it more P-shaped or less P.
It's not. Okay, so guys, SP. When we SP hybridize, notice that these 2 P's just sort of magically fade. We'll talk about what really happens in a minute, but we understand those 2 p orbitals are not hybridizing. When these hybridize together, how many hybrids will we get? There they are, around the same nucleus. Linear domain geometry. You get it? Okay, so now let's move beyond the 3 P's and let's bring in the D. And with that D, they will all necessarily hybridize. We get 5 hybrid orbitals. These 5 hybrid orbitals around the same nucleus explain the trigonal bipyramidal structure. Similarly, with 6, we bring in 2 of the D's. These guys hybridize. We end up with 6 domains, hybrid orbitals, and an octahedral structure. Go ahead.
Is there like any relation between which P is
Yeah, you know, I'm going to guess yes, only because they apparently vary. It appears as if they specifically chose, first of all, the one with the donut around the middle, and then that other one that was... So the answer could be yes. I can't explain it, and I've never had it explained to me, but I wouldn't be surprised if the answer is yes. But I'm frankly not sure. Yeah. So guys, you okay with the idea of hybridization and how it then relates to these 3-dimensional structures, these domain geometries? You're good? Okay. So now guys, what we're going to do is this. we're going to talk about what happens to that p orbital that doesn't hybridize in sp2 hybridization, and what happens to the two p orbitals that don't hybridize when something goes sp. Now, in order to do this, what I'd like you to do is I'd like you to draw a Lewis dot structure in your notes. Did any of you print the notes today? You guys don't do that, right? You just like to take notes. That's good, because we have so abandoned the notes that I posted that we may as well not even really start. Well, we'll start Keynote again, but you'll see. We'll go here for now. Okay, so guys, with all of that said then, let's do this. What's a good example? Okay, let's do this. C2H4. Draw the Lewis dot structure. I've never done this way. Like I said, this is always different. This is turning out well. Did you get it? So guys, obviously I know what this is going to look like, right? I chose it. I would imagine that you've muddled through it. What I'm going to do though, and certainly you would need to do this on the test, I'm going to draw it as three-dimensionally correct as I can. You'll see why in a minute, and if yours isn't, that's fine. But guys, in the end, this is what this molecule looks like. The carbons are double bonded together, right? You okay with that? So guys, let me ask you a question then, and please try to answer this on your own, not out loud, but try to answer this on your own. What is the domain geometry of the carbon on the left? And then what is the domain geometry of the carbon on the right? First of all, do you see that it's the same? And what is it? Trigonal planar. Is that okay for everybody? That even a double bond counts as one domain, and so consequently this carbon has three domains, making it trigonal planar, and the other carbon, the one on the right, also has three domains, therefore it's trigonal planar. You okay with that? Now try this. What is the hybridization of the carbon on the left and the carbon on the right? sp2. Some of you aren't sure, but guys, the idea is this. If you've got three domains, the hybridization has got to be sp2. Maybe we should talk about it. So the thought then being, here is one sp2 hybrid orbital that is bonded to a hydrogen. Here is another sp2 hybrid orbital that is bonded to a hydrogen. Here is another sp2 hybrid orbital that is bonded to the neighboring carbon. Then similarly, here's an sp2 bonded to a hydrogen. Here's an sp2 hybrid orbital bonded to a hydrogen. And then here is this carbon's sp2 hybrid orbital bonding back to the same carbon, the other carbon, which is also sharing an sp2 hybrid orbital. Does that make sense? You're okay? We can even label it, and I think, oh, that could be in the way. Let me do this. Maybe, let's go down here. So this is an sp2 hybrid, and this is also an sp2 hybrid. Guys, it's critical that you're settled with that. So ask questions if you need. You okay? Taylor, you okay? Yeah? Okay. Now, guys, I'm scared to death, so I'm not going to do this. I'd really love to be able to switch to the video now that we just watched the website and show you again the animation of sp2 hybridization, but I fear if I leave this, I'll never get back. So let's just sort of talk our way through it. Remember when the video started, we had the 1s and the 3p's, right? And if it went through sp2 hybridization, what happened first? That p faded away, remember that? And what did I tell you happened to the p? Does it really fade away? It doesn't. It's still there, but it's not hybridized, right? So guys, what does an unhybridized p orbital look like? A dumbbell. So now, what would be a good color? Let's go black. We still have an unhybridized p orbital right there. And we still have an unhybridized p orbital right there. And guess what these unhybridized p orbitals do? They link together top and bottom, and they create the second bond of the double bond. Crazy, right? But guys, that's what happens. So when these double bonds form, what happens is an unhybridized p orbital from both of these atoms overlap together above and below the plane of the molecule, and they form the second bond of the double bond. Now guys, here's the unfortunate part. We don't represent that very well when we do Lewis dot structures. See, this guy right here is pretty good for the first bond of a double bond because that first bond really is in between the nuclei. But the second bond of the double bond is not in between the nuclei. It is above and below the plane. We still just draw the line just for simplicity's sake. But that second line has nothing to do with what this really looks like. It is very much a looping around bond that exists both above and below the plane. And guys, these bonds have names, and these you do need to know, and this is going to sound familiar. These bonds right here, these single bonds, are what are called sigma bonds. And guys, I'll write it down for you. Sigma is this Greek letter. It's an O with a pigtail on it. Those are what are called sigma bonds. Single bonds are sigma bonds. Guys, you may know this is sigma, right? Which means some. This is uppercase sigma. Did you guys know that Greek letters have upper and lower cases? This is uppercase sigma. This is lowercase sigma. Now, what about this double bond? Well, guys, this bond right here is a sigma bond. It is formed by sp2 hybrid orbital overlap. Now, guys, what about this bond that we've drawn in black that is above and below? This is what is called a pi bond. And a pi bond is created by unhybridized p orbital overlap. So the bottom line then is this. If you've got a single bond, that will be a sigma bond. If you've got a double bond, that is a sigma bond and a pi bond. If you've got a triple bond, that is a sigma bond and two pi bonds. And we'll look at that in just a minute. You guys okay? Let me show it to you. This is the worst video you'll ever see in your life, but it's actually the best video that I've found to show you what we're talking about. I can't imagine the grad student that put this together. It gets worse. Okay. Wait, come back. Oh, better come all the way back. Right, okay, there we go. Guys, they are going to show you the formation of a C2H4 molecule. So let's look at what we got. This in the middle is the carbon. the nucleus of the carbon. What do these three purple lobes represent? sp2 hybrid orbitals. What does this red thing represent? An unhybridized p orbital. And what do these turquoise things represent? Hydrogen atom bonded to two of the sp2 hybrids. Keep your eye on the prize. So here we go. Continues to, oh my gosh, boom, stop there. What kind of bond is this between the carbon and the hydrogen? Sigma. It is an sp3 hybrid overlapping with the 1 electron in the 1s in hydrogen. Similarly, back there, you can't see it, there's another sigma bond between another sp2 hybrid orbital and the electron in the 1s of hydrogen. Same thing going on over here. Now guys, what is overlapping here? It's a sigma bond, but what is overlapping? An sp3 or an sp2 hybrid orbital from each of the carbons. That forms a sigma bond. Again, what do the red things represent? Unhybridized p orbital on each carbon. These guys wrap around top and bottom, and that is what a double bond looks like. This is actually the computed representation of electron density for a double bond. You've got this, which is a sigma bond representing the overlap of the sp2 hybrids, creating a region of increased electron density in the bond axis. We call that a sigma bond. And then above and below, you've got the regions of increased electron density from the unhybridized p orbital overlap happening here and here. And the sum of that, if this will let me do it, the sum of that is the sigma bond there and the pi bond there for a double bond. Go ahead.
Do they call them pi bonds because of two semicircles and semicircles?
I don't know. I'm not sure. Let's go with yes. That's exactly. I don't know. But you should know that when they tried to teach me radians when I was in high school, I rebelled with all I had because I still don't understand why they do that to children. So, okay. So guys, as if it couldn't get better, it gets better. We've already done, actually we haven't. Let's do this. Let's do C2H2. No, we're going stills on this, yeah.
So, if that's what happens to the p orbital,
Yeah.
something special happens to the p orbital?
No, because remember for the most part, so here, no. Because if we did, we would necessarily have to have like quadruple bonds and pentuple bonds, and that can't be. You just get too much interference, and you'll see why in just a second. So guys, C2H2. I'm about to show you just how bad of an artist I really am. So, forgive me if I'm giving something away, but you've got hydrogen, carbon, triple bond, carbon, hydrogen. So guys, let's have this conversation about 11 different ways. You ready? First of all, what is the domain geometry around either one of these carbons? Linear, right? This carbon, 2 domains. This carbon, 2 domains. This is a linear molecule around either one of the carbons. If it's a linear molecule, what does the hybridization have to be? Good. So this is an sp hybrid, and this is an sp hybrid. You good there? Okay, now let's talk about the bonding that we see. What kind of bond is this? Sigma bond. What kind of bond is that? Sigma. Now let's focus on the triple bond. What is the first bond always? Sigma, and then the other 2 bonds are pi bonds. Now the question is this: how could this form? Well guys, now let's take this back to hybridization and this is going to get messy because this is an sp hybrid. And so this represents the overlap of one of those hybrid orbitals with the 1s electron from hydrogen. And then, yeah, you get it. So that sigma bond is representative of the overlap of one of the sp hybrids, and then that is the overlap of the other sp hybrid. But if we could again show the website with the video, we've got the 1s and the 3 p's. Is that the way? Whatever. And then as they hybridize, it was actually this way. What happened to the p's first? 2 of them faded away, right? It was just 1s and 1p. So what happened to those p orbitals? Well, guys, I didn't want to do that. Let's see if it'll let me do this. So what happened to those hybrids? We actually have one here, and then we have, where would I switch colors? I'll do it this way. And then coming back, we will go green. And then, guys, this is supposed to be 90 degrees. Yeah. And no. I need to draw these smaller. So 90 degrees, forgive, I mean, you get the idea. And then, guys, what happens is these things overlap twice. So these that are in the same plane create an overlap, one of the pi bonds, and then the other p orbital, unhybridized p orbital, that is 90 degrees to that one, creates another pi bond, and you end up with the triple bond forming. You get the idea, but maybe this makes that a little more clear. Yeah. But again, you've got the sigma bond here. You've got one pi bond that is above and below the axis, and then the other pi bond, which is 90 degrees to that. You get the idea? Okay. So guys, now let's have an aha moment. You ready? Clean sheet of paper. Draw benzene. If you don't know what benzene is, you need to know what benzene is. Benzene is C6H6. But guys, we're going to draw benzene in a little bit different way. So we've got, do this with me, carbon, 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 carbon. Just do this with me. You single bond everything together. And then, guys, place a hydrogen like so. Okay. We are now going to do, well, no. This will be even better. How many electrons do we have on the board? It's hard to count, but let's start. We'll finish on this one. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Got 24, right? How many electrons total do we have? 24 plus 6 is 30. So we've now got 6 extra electrons. Let's put 1 electron on each one of the carbons. Now, guys, this is where this gets interesting. Look at any one of those carbons. You know what? Maybe I should have asked this first. Don't erase yours, but I'm going to erase mine. And I'll put them back in a minute. Look at any one of these carbons, just given the bonding. Can I go straight to hybridization? Or should we talk domain geometry first? What's the domain geometry? How many domains on each carbon? 3, right? Each one of these carbons has 3 domains. So what is the domain geometry? Trigonal planar, what is the hybridization? sp2. Now watch. Let's put back, I wonder if I can, I don't think I have a redo. I'm just going to have to redraw. No, that changes the whole page, unfortunately. Yeah. So guys, let's put this electron back. And now here's the interesting question. Where is that electron? If these are sp2 hybrids, follow the thought. If these are sp2 hybrids, where is each of those electrons? Guys, follow the thought. sp2 hybrids. What does each one of these carbon atoms has that is not represented if they are each an sp2 hybrid? One unhybridized p orbital. Are you not convinced these are sp2 hybrids? Are you okay with that? Okay, if they're sp2 hybrids, each one of them has an unhybridized p orbital. That's where that one electron is. And what happens to those unhybridized p orbitals in benzene? They wrap around completely, top and bottom, around the entire molecule. And what do we call that phenomenon? Delocalized pi bonding. Do you get it now? That's the whole idea. Pi bonding, which you learned previously, delocalized pi bonding is the delocalization of a pi bond. How do pi bonds form? Unhybridized p orbitals, and in this case, these unhybridized p orbitals wrap around the entire molecule, resonance stabilizing the entire molecule and creating these delocalized pi bonds. You get the idea? Yeah? That's the idea, and that's exactly the idea that we draw it like this to represent that that unhybridized p orbital goes all the way around the ring. Yeah?
So does that mean if we look at graphene and it looks the orbitals, if we look at all the orbitals, it will look like the sea of Cheerios?
I don't know. I'm not sure. So guys, let me show you what you need to be able to do with this. I think that this has been interesting, if nothing else. But guys, the bottom line is there's stuff you've got to be able to do. So we have enough time that I can let you drive formaldehyde. This is actually the molecule that they used to use for a long, long time to preserve lab specimens. Formaldehyde is polar enough that it's a liquid. You'll see why after you draw it. How was that for a little foreshadowing into the next unit? Formaldehyde is polar enough that it's a liquid. It also turns out that it works well to slow the biologic processes that cause things to decay. And so they would take lab samples and they would put it in glass jars full of formaldehyde to keep it from decaying. It smells horrible. Well, I don't think they use formaldehyde anymore. I think they found things that are less volatile and so less stinky. But guys, drawing this properly, or at least carefully, you find out that formaldehyde looks like this. So you ready? I got all sorts of questions for you about this molecule. First of all, what is the domain geometry of that central carbon? Trigonal planar. As such, what must the hybridization be? sp2. What about this? What is the hybridization of the oxygen? What is the hybridization of the oxygen? How many domains? 1, 2, 3, sp2. What happens to the unhybridized p orbital that you just identified exists on the carbon and the oxygen? Forms the pi bond and the double bond. Get the idea? What about this? What's the hybridization of either one of those hydrogens? It's not. Hydrogen cannot hybridize. It doesn't have any p orbitals. Okay? So when hydrogen forms a bond, in this case with carbon, what's happening is this bond is representative of an sp2 hybrid orbital connecting with the unhybridized 1s electron in hydrogen. So we've established that this is a trigonal planar molecule. We've established that this is an sp2 hybrid for both the carbon and the oxygen. The hydrogens are unhybridized. And then, guys, this isn't something that, well, actually it is. What about polarity? Is this molecule polar? In which direction? Towards the oxygen. In this case, it is polar, like so. And again, as I was sort of muttering about earlier, that's what makes formaldehyde a liquid at room temperature, because the molecules are polar enough that the intermolecular forces allow it to liquefy even at room temperature. So there you go. You guys good? Yeah?
So what would tin like before?
Um,
So that's
tin. So we'd need to draw the Lewis dot structure first, right? So is it just, oh, I see what you're saying. So let's try it. So it's Sn, and then you've already drawn this, right? Is that it? Okay. So keep going. Right. You are, exactly. So we would understand that this is bent, right? It's not trigonal planar because you've only got, so it would be, let's do this. It's trigonal planar in domain geometry. Would you agree with that? Because there's 3 domains. So we understand then that it's an sp2 hybrid. Let's just keep rolling and then we'll come back. But because 2 of those domains are bonding domains, we would understand that the molecule's bent. You okay with that? I know this doesn't answer your question, but are you okay with those ideas? Because this brings up an important point in my mind. We just did this whole hybridization conversation, right? And what is it that we use to predict hybridization? Domain geometries. But do you remember that throughout this entire unit we've said domain geometries are not a concept that show up on the AP curriculum? So when you see the test on Tuesday and it says, what is the geometry for this? If you add that molecule, it will simply say, what is the geometry? The answer is bent. The answer is not trigonal planar. We don't talk about domain geometries as we're answering questions. They're instructive for us because they help us understand 3-dimensional geometries and now hybridization. But guys, we don't talk about domain geometries, only molecular geometries. You okay with that? So now let's answer your question. There's a p orbital here that's vacant. Okay, this is an sp2 hybrid. We understand that from the domain geometry. And what we've got here then, and this is one of those weird examples of a molecule that doesn't fulfill the octet rule. It only has 6 valence electrons. And so what functionally happens is it's an sp2 hybrid with a p orbital that is vacated. There's nothing to put in there. So it can't form a double bond. Yeah. There are no electrons in it. Oh. Okay, keep going. Say that again. I wasn't tracking with you. Right. Well, yes, but you have the potential for it, and it's actually not present because it's not necessary. Yeah. Correct. sp2 with two electrons in it. Correct. Yeah, that's right. So if we want to map it out, we could do like we were sort of doing before. We could go like this, and we can say that this is what tin looks like before it hybridizes, and then after it hybridizes, it does this, and it forms three sp2 hybrids. You've got 2 electrons in one electron in each of the others. These are the ones that bond to the chlorine. This never hybridizes, and so it's not even a part of the conversation. Is that okay? No, and that's not the case. It will actually be more bent. Similarly bent, because just because that unhybridized p orbital is vacated, it doesn't change the structure, because the only thing that it would do is hold it flat, because it exists above and below. Do you see what I'm saying? So, guys, that's a great question. Hey, we've got about 3 or 4 minutes left. Guys, we will very quickly grade this homework next time with the understanding that the thing that you really need to be able to do is describe hybridizations. This is your homework. Ask questions if you need prior to Tuesday. We'll take the test on Tuesday. Uh-oh. Huh. I did start recording, right?